So I'm going to hand over to Michael and Calum from Samsung, who are going to speak to you about living long and optimizing.
Hi, so I'm Michael and I'm here with Calum. We're graphics engineers in Samsung's game ecosystem team. Basically, basically we work with developers all around the world, both supporting companies remotely and locally. Our main focus is on getting Vulkan out there on Android. So a lot of the titles we work with are kind of the top-end titles. So we're using Vulkan to really get the most out of the game. And today I'm basically going to go through a couple of the practical problems and things that we've run into actually working with these developers. So yeah, let's get started. So the first thing is kind of what seems like it might be quite a straightforward topic, swap chain management. Interestingly, on Android, there are a few problems with this, and I'm going to cover them in more detail as we go on. So those of you who are familiar with Vulkan probably know there are three ways of interacting with your swap chain. vkQueue next image will return the index of the next available image. vkQueue submit workloads, render workloads and so on. And vkQueue present to tell the presentation engine that you're done rendering and are ready to present an image on screen. Now, according to common knowledge, vkQueue image is a blocking function. It can block if there's no image available. This is fine. This normally only happens when the CPU is too far ahead of the GPU and we need to wait for the GPU to catch up with its work. QSubmit, non-blocking, you just kind of fire off work, say, okay, here's command buffer, we're releasing it to the backend driver so that it can consume some work. And similarly, present is normally considered to be non-blocking. But this is where the problem lies. On mobile, we actually find that present frequently blocks. And this is something that surprised us and surprises a lot of the developers we work with. Oddly enough, it's become a really major performance bottleneck for titles that don't really anticipate it. And today I want to go into a bit of detail about why this is happening and considerations you should take to avoid it. So this is what a standard swap chain implementation might look like. We've got acquire image. We need to know the image index that we're going to use in order to encode our frame buffer so that we know exactly what we're rendering to. So we normally do that before we start recording. Finally, once we've finished recording our commands, we'll submit the image and present the image. And this is all fine. If we've got a standard frame time here, we're not really using the CPU too much. Vulkan's very lightweight. But we start running into problems when we hit the blocking behavior of these problems. If we're working in a sort of single thread or a single graphics thread environment, we can quite easily run into a situation where frame by frame we have unexpected delays as a result of these functions being called. This is especially prevalent with the present image function. Because again, this is something that can block for quite substantial amounts of time on mobile, and it's something that you may not expect, and it's something that may take you by surprise, cause sort of unnecessary stuttering in the title, and so on. But the first consideration is what's a good way of dealing with acquire. So one thing we kind of recommend doing is what we're going to call a delayed acquire. The idea is that in most game environments, you only really need to know the image index at the very end of your render workload. Normally that's, say, if you've got some post-process, it's only that final render where you're actually rendering to some output swap chain image. And so we can delay acquire as long as possible to give the system enough time to ensure that image may be available. This is only a small change, but it can make the difference and it can smooth out your frame rate. We also have the option of attempting acquire early as well, and the idea there is that if we get the image early, we may be able to start encoding and preparing some Vulkan objects ahead of time, which can again smoothen out our frame rates. And all of this becomes really important on mobile when we're targeting the absolute sort of pinnacle of performance and user experience. To go into a bit more detail about the issue I mentioned with QPresent blocking, this is a systrace capture. A few of you who are on mobile may have used this tool. Basically gives you information about the Android OS and the associated cost of calling certain functions. What we can see here is actually QBuffer, which is the internal function called by QPresent, is taking around 12 milliseconds a call. And that is ludicrous. That's absolutely insane. And we were just amazed with the number of games that were running into this problem. Sort of maybe 50% of the games that we look at have at least some degree of issue with this. And while it's not consuming excess CPU resources, the way most games are coordinated, this actually culminates in an unexpected delay and an unexpected stalling, which hampers your ability to get on with other useful CPU work. So I'm going to sort of go through two quick solutions to this problem. And these are really just things that you can throw in. And the first one is a delay present. We found that one of the causes of this issue, and this is related to the OS and the driver interaction, is that the closer you call present to submit, the longer this delay ends up being. A simple solution is just to delay your call to present right before your next frame submit. And the idea here is that we're not actually delaying when the image will be shown on screen. We're just delaying the calling of the function to a point where the image is likely already available from the GPU. So the second that we call present, the image is already rendered and it can instantly be flipped over to the presentation engine without the presentation engine having to stall on any weird internal problem. And this can give us a huge reduction in stall time, down from 12 milliseconds to about 0.2, which is exactly what we want to achieve. Oh, great. Thank you, Microsoft. You always know how to... Oh, no, this is on. Right. So, anyway, perhaps a more Vulkan-specific solution is the idea of using a separate thread. And this is something that might be relevant to desktop as well. And while Swapchain is not really something you're going to run into that many problems with on desktop, there is a certain nicety to managing your workloads in this way. The idea here is that we defer all of our Swapchain interactions to a secondary thread. This means that it's completely decoupled from our command buffer recording, our Vulkan object preparation, our resource staging, whatever it might be that you're doing. And the real benefit of that is that there's definitely no reduction in throughput of your heavy graphics workload by unexpected or inconsistent frame changes. And this becomes quite relevant if you've got a game with a highly variable frame rate. For example, we find a lot of Unreal Engine titles have frame rates all over the place. They can flip from being CPU bound to GPU bound frame by frame, depending on whether sort of shader compilation or resource preparation is happening. And this can lead to a really inconsistent frame rate. And it can also mean that some of your Swapchain images are just never available when you need them. And a solution like this just kind of helps stabilize everything out. You'll still need some form of synchronization point, but again, the idea here is that we're always using our CPU threads for effective work rather than wasting valuable time just sitting around doing nothing. Looking at some performance figures from this change, so this is running on S9 Adreno chip, and just from implementing this second thread, we got an increase from 34 to 41 FPS. And again, the main reason I'm stressing this is that this is just something that people can completely miss. It can come out of the blue. All major game engines that we've worked with have this problem. And so just implementing a simple workaround like this can actually give you a huge performance increase that you just may not have expected. But yeah. So the next thing I kind of want to cover is how we can look at the workflows and exactly get an idea of what the process is doing and how we can improve that. So this here is a sample trace from Serious Engine. So Chris talked about them as a Vulkan partner who we've been working with, and basically what we can see here is we've got a trace from ARM's Streamline tool, and this basically tells us exactly what the GPU is doing at a really low level, a really microscopic level, to give us that high detail. So we've got a frame here, and we can see that we've got a bit of a problem because like while the GPU is always doing something, it's always doing either vertex or fragment work. It's never doing those two things in parallel, and therefore there's an opportunity to do better. The main reason that we're having this issue is from suboptimal pipeline barriers and subpass dependencies. In Vulkan, it's really, really important that you get this right. Each interaction, each render pass will have its own dedicated dependencies between each stage, and it's up to you to identify what the requirements of that render pass may be, and kind of manually tweak these pipeline barriers to get the absolute maximum performance. Again, this is really important on mobile because we're trying to squeeze out every inch of performance, make sure that we're using the hardware to 100% where we can, especially the GPU. We really want to maximize that just to get the highest frame rate you can manage. And if we look at this scene, for example, it's a decent looking scene. This is ported from desktop, and it's only running at around 16 FPS. So that's a frame time of 62 milliseconds, which isn't great. That's not really playable yet. And we've got to do a lot of work to get that to a point where it's even remotely fun. So a quick overview on what pipeline barriers are. So pipeline barriers are used to create execution dependencies between two pieces of work, or rather specify them. We do this with two masks. The destination stage mask basically says where a secondary piece of work is going to wait. So if you've got a shadow pass or something, we can specify the stage before the that stage will start waiting for a second stage to be ready. And I'll go into the detail with this in an example. But for graphics, these are a couple of the stages that we care about and the ones that we can control. And these are essentially the stages that we're going to use to really control the interactions between rendering. So to simplify just one interaction from that scene, we're looking at the main render passes, the interaction between the shadows and the main scene. Naturally, when we're doing shadow mapping, it's important that the shadow data is available to the main scene at the time that we're rendering it, because we need to use that shadow data to cast shadows on the objects. And therefore, if we set up sort of a naive pipeline barrier that just guarantees that all of the shadow map rendering will be done before we start the main scene rendering, we can guarantee that the shadows will be available. And this is correct, this works, but it's not optimal. What we can see is that when we actually break down the pipelines and look at the stages we have available, we can see that we only need the shadow map data by the time we get to the fragment stage of the main scene render. This means that we can actually be getting on with doing the main scene's vertex work while we're still busy finishing up the shadow map rendering. And we can achieve this with pipeline barriers using something like this. If we set the destination stage to vk pipeline stage fragment shader bit, that basically tells the GPU that we can go as far as the fragment stage before we need to start waiting on any piece of work. Because we know that we're dependent on the output from the shadow map stage, then we can set the source stage to color attachment, which implies that we can release from this stage once that color data is available. So we'll go as far as the vertex, stop, wait for the shadow map to complete, and then once that is ready, we can carry on with our workload. And what this means is we get much better parallelism in the GPU. We can really saturate the hardware, make sure it's doing exactly what we need it to do, and have both of these highlighted sections running in parallel. Now, if we go back to our original example here, what this looks like is we've now shifted this main scene block over so that we don't have a dependency between the vertex work and can start it immediately. What this culminates in is a 6 millisecond saving. And all we've done here is just made sure that the GPU is busy. But 6 milliseconds is a lifetime in terms of frame rendering, and getting this right is therefore really important. Looking back at the original trace, we've got our original frame here, and we can see now that we've got a much more reduced overall frame time. And the main thing we see here is that we've got a really good overlap between the vertex work and the fragment work, and that's exactly what we want to achieve. And in this case, we've looked at every single render pass in the game and identified the dependencies between them. The original had dependencies on vertex texturing, which we realized weren't actually even a feature in the mobile version, therefore we could just completely remove that dependency. And what this has culminated in is a 56% performance increase by essentially just changing one line of code. And that's exactly what we're looking for in these scenarios. So we're now down to 40 milliseconds frame time, down from 63, which is obviously a really, really nice saving. Another couple of things we can look at here are maybe stages that we don't need. Again, we can use Streamline to give us a really detailed breakdown of exactly what's going on. One common thing, especially when you're working with a desktop engine, is a depth prepass. It's quite reasonable if you've got a very fragment-bound game that you kind of do a first depth prepass to eliminate out all of the potential overdraw rendering that you won't need, meaning that you'll only ever render your pixels one time. You'll only ever run a shader one time per pixel on screen. On mobile, because we're working with tilers, we almost get this behavior for free. And this is because each tile is rendered on a small scale, and each pixel will only run one invocation of the fragment shader at the end of its execution anyway, because we get this sort of depth evaluation inherently built into the hardware. And that means that on mobile we can essentially just remove this stage. It doesn't add any value and just slows us down. If we do need, another reason we may need this is because we need contextual depth information for the scene. Again, on mobile, because we're working in tile-based architectures, we can actually take advantage of Vulkan Swapasses, which is the next topic I want to cover, and we can basically achieve this for free. Again, occlusion queries are another thing that are really common on desktop. We have high detailed models, high quality geometry. We want to try and eliminate as much upfront drawing as possible. On mobile, we tend to be working with smaller LODs, and geometry is generally very expensive on a tiler, which is the one downside. So one thing that we want to do is actually just disable the occlusion queries altogether, because they end up just being slower and don't really give us the saving that we want. And so when we remove these excess features that we don't really need, we can retain identical frame quality but get a sort of substantial increase in performance, down from 40 milliseconds after our previous changes to 28 milliseconds. And now we're looking at a game that's actually running at a really nice playable FPS. 35 FPS is more than acceptable on mobile, and we haven't sacrificed any scene quality at all. We've retained identical visual quality of the game, and all we've done is just evaluated our workloads and determined what's necessary, how we can improve those interactions between different stages, and go from there. The next stage is subpasses. So this is something that doesn't come up too often. Not many people are really using these yet, but I want to try and change that by giving you kind of a use case of where these become really relevant. The idea on mobile is when we're working on a tile-based architecture, memory bandwidth becomes quite a big problem, and we want to try and find ways that we can minimize that memory bandwidth as much as possible. One way of doing this is with subpasses. So the idea here is that rather than writing data back to main memory and reading it in again, we can keep local data such as depth information, normals, lighting information, whatever it might be that you need throughout your rendering process. We can keep that information on tile and never actually have to write it out to main memory. And this can provide a significant increase in throughput for those kind of effects, especially if you're dealing with quite heavy G buffers and sort of lots of pixel data in your frame buffer. This is an example using Unreal Engine. Unreal Engine uses a high-level node-based shading language, and one restriction of subpasses is naturally that you can only use the information that's available per pixel. For example, because we're working with small amounts of data on tile, subpass only works if a secondary subpass, such as a translucency pass, uses the same data that was previously rendered. So one common thing here in Unreal Engine 4 is the translucency pass. And the idea here is that we do our main scene render first. Translucent objects are dependent on the per pixel local depth. So for example, if you're doing a depth fade or a water fade effect, soft particles, something like that, you need that depth information there. Normally on desktop what you might do is write back your entire depth buffer and then sample into that in a secondary render pass. On mobile we can completely avoid this overhead and just immediately have that depth information available, and all we're doing is slightly fragmenting our workloads, but we're not having to do that expensive write back that we'd otherwise need to. Now it's quite easy to see in Unreal when you've got shader nodes such as pixel depth whether a shader would be compatible with subpasses. But if we don't know and we're trying to see whether our game is compatible and we're trying to identify if a particular shader could be converted to a subpass implementation, we can do a simple test like this. So here we've got something which is sampling the depth texture. We don't really know where it's sampling. From that code we can look at it and be like, oh, we don't really know what those constants are. We don't really know how that array data is manipulated. We could be sampling all over the place basically. But just by doing a simple diff check and seeing if our entire rendered area doesn't actually deviate from the local coordinate sample that we're testing, then we can identify, oh, actually this shader could just be run in a separate subpass. And immediately we've now just eliminated the need to write back data to main memory, and this is really significant. If we look at the traces showing the difference, this top trace is just using the standard Unreal Engine 4 render pass, and over the course of an entire frame, and again these tiles are being written out progressively, we end up spending an extra millisecond idle throughout the entire frame when we're writing back through various subpasses, and this is just from writing back the color depth and normal information on a per pass basis, and then naturally reading it back in later on. Using subpasses, we don't need to do that write back, and our idle time goes down to 0.15 milliseconds, which is a pretty nice reduction. The other major thing is the bandwidth saving. So we've now just basically saved 700 megabytes per second, which is quite a substantial chunk of our overall bandwidth budget. When we look at the performance impact here, we've gone up from 52 to 55 frames per second. It's not a massive increase, but when you're kind of at the very limit of what you're trying to do to optimize your game, even getting a 6% increase like that can be really substantial. And again, this is basically just for free. All we're doing is reducing the amount of work having to be done and the amount of interactions with our memory. And this ends up being a really nice saving. So in this case, the CPU usage has gone up a little bit, but that's mainly because we're now pushing 3 extra frames per second, and there's a CPU cost associated with generating a frame. So yeah, that's Subpasses. I'm now going to hand over to Calum, who's going to go through a couple of quick tips and tricks. Thank you.
Hi, I'm Calum Shields. I'm an engineer at Samsung UK's Galaxy GameDev team, and for the next few slides, I'm going to take you through a few more small but no less important optimizations for mobile. So first off, load and store optimization. So typically I find that desktop developers will get this wrong because in desktop you don't really need to worry about this because you'll be reading and writing from memory anyway, so you just set it to load and store and forget about it. But in mobile it's really important to get it right, because so if you're doing a load, then you're reading from memory, but if you do a clear or don't care, the value's just set straight into tile buffer, so it costs no bandwidth. And then store, again, you're writing out to memory, but if you don't care, it gets discarded, and it costs no bandwidth. So yeah, just to give a basic example of how it should be done. So if you're doing like forward rendering to a back buffer, you want to clear your depth buffer, clear your back buffer, then store the back buffer. Don't care in the depth buffer because you're not going to need that depth information after the fact. So yeah, while we're on the topic of clearing, please, for the love of God, don't use these color clear image commands. Again, desktop, it doesn't really matter because.
Nice. You don't want that to be there.
Okay. Anyway, well, I mean, if you're clear in any of these, you're clearing your clear value gets written to the memory anyway, so it doesn't matter as much. But in mobile, it's used different because only these two will write to memory, whereas, as I already mentioned, load.clear will set your value in tile buffer, and same for the clear attachments. Between the two, best practice is to do a load.clear at the beginning of the render pass, and then use clear attachments if you need to clear in the middle of the render pass. Most likely, you'll only need to do that if you're using subpasses, so if you need to clear before you move to the next subpass, you would use that. So transient attachments are really a mobile-specific feature. It's designed for attachments that are never written out to memory, because they won't. If they're not written out to memory, you don't actually need to have any memory reserved for them, so you can make them transient, and it saves you some space in memory. This really goes hand in hand with subpasses, because, for example, if you're using deferred rendering, then all your G buffers can be kept entirely in tile memory, so you don't need to write them out at all. But even outside of subpasses, it should still be quite useful for depth attachments, because they're something that often don't need to be written out either. Okay, so staging buffers, this is something that quite common practice on desktop, rightly so, because you need to copy your buffer data from system memory into video memory to get best GPU performance. But on mobile, it's a unified memory architecture, so as you would expect, this stage is completely unnecessary. So you can just use the initial buffer you load your data into straight away. It is worth mentioning though, this only applies to buffers. So for images, you'll still need to have a staging step in order to get your texture data into an optimally tiled image. Just to give you an explanation of how tiling works. So linear tiling is when you've got your texels arranged in consecutive order in memory, row by row, like so. And so this is also really good for CPU access, because your text is arranged in a predictable fashion, but it's not as fast for GPU as it could be, which is why we have optimal tiling, which is a implementation independent method of arranging the texel data in memory to be more cache friendly. So you should be using optimal tiling for your texture data wherever possible. And finally, depth stencil resolve. This is a new Vulkan feature, which was released earlier this year. It was being worked on by popular demand from developers. So if you're not already aware, multi-sampling is pretty cheap on mobile, because you can resolve your multi-sample data in the tile memory and just output the fully resolved image. But currently that only works with color attachments. So these depth-dependent effects that are listed here, they can't be done with multi-sampling because it's just far too costly to do. So that's why then we have this extension, which now allows you to do your depth stencil resolve and tile memory along with the color attachments, allowing you to do these with multi-sampling at no additional cost. Okay, so for these last few slides, it's going to quickly take you through some of the tools we use for identifying performance bottlenecks. So yeah, RenderDoc. I'm sure most of you are already familiar with this anyway, but for those of you who aren't, RenderDoc's pretty much the gold standard for Android tools at the moment, and it's great. I love it. It gives lots of great information, really well laid out. It lets you, step through your draw calls and see all your pipeline stages and what the states that they're in. And best of all, it's free, so you have no excuse not to be using it. Streamline and Snapdragon profiler. So these are your profiling tools. They're pretty much crucial for identifying performance bottlenecks. And they both do effectively the same thing, just for the respective chipsets. Again, they give lots of great information, like your per core, per threads, CPU utilization, as well as your vertex and fragment loads. And they both have a CPU trace on them as well, so you can help to identify where your hotspots are in your code. And finally, GPU Watch. So this is a Samsung developed profiling tool. It's built straight into some of our Galaxy devices, so there's no requirement for any desktop clients, and you don't need rooted devices either. So you just get like an overlay, like you see here on top of your game, and it gives you like the most useful information you want, so your frame rate, your CPU, GPU utilization. So it should also be useful to you if you just want to do a quick profile of a level in your game. You don't want to set up anything. And that's the presentation. Thank you all for listening. So a quick recap, because we've gone through quite a lot of stuff. They say you can only remember 3 things at once. So these are the 3 things you should remember. And these are the 2 that will be in the quiz. Any questions?
How is the depth resolved for MSIA? It's not averaged, right? So do you specify some mode like min max, or
You can choose. So for depth, there's only one mode that's guaranteed to be available, and that is to simply pick the 0th pixel. So for example, if you've got 2x2 multi-sampling, it will take the top left pixel essentially. Okay. According to the spec, there are other modes available like min, max, average, stuff like that, but they're not all supported on every platform. So yeah, and it's kind of up to you to decide whether averaging depth makes sense or not.
yeah?
Just a comment on the flipping stuff that you did at the beginning. The Vulkan tutorial teaches you absolutely the wrong way to do it. And it really annoys me that it does that. I mean, I know why it does that, because it's trying to teach you how to use Vulkan, but the fact is nobody ever wants that to be in their app in the way that it's taught. So it would be really nice if anyone can to put that in the tutorial. It needs at least extending to say, okay, we've just taught you how to badly flip. Here's how to do it.
I think one common thing in the tutorials is having, if you've got regarding swap chains and stuff, is having like the command buffer tied to a particular swap chain image as well.
Yeah.
And that's where a lot of people hit stalls, because the command buffer might still.
Yeah,
it actually you hit a fence. Or something.
Yeah, it hits the absolute worst case. That's what they teach you.
Yeah. I think there are good tutorials out there as well.
And I recently ported an app from DX12 to Vulkan, and I couldn't. I found there was so many samples. It's hard to know which one to look at. Which one is the best approach.
Any other question? Yeah.
Yeah, I have a question about the Q% performance issue. Does this depend on whether you have double buffer or triple buffer swap chain?
No, it's independent of the actual size of the swap chain. So acquire will be affected by the size. So if you have more swap chain images, then acquire will block sooner if you have less. and not block if you've got more, because there'll always be more available. But regarding QPresent, it's not really supposed to block. It's essentially a kind of OS. It's an odd OS behavior, and we can't go into the exact reasons as to why it happens. It's mostly just an awareness of the fact that it happens. So it's kind of an unexpected delay. Partly, so one side of it is caused by the OS's frame pacing mechanism, and another side is caused by the driver interaction, but the exact details of which are quite intricate. But the important takeaway is that it does happen essentially, and the best kind of way of alleviating it is to either use one of the two methods that I talked about, so either the delay present or the like bumping it off to a separate thread to absorb the weight. Does that answer your question?
I'm just wondering if this will be fixed at some point.
It's something we're definitely working towards. It's not just a Samsung issue. Every single Android device we've tested on it seems to happen on. Yeah, it's definitely something that we would like to resolve, but when that will happen, I wouldn't know for certain.
Yeah, as in we are discussing it actively with Google, so it's not like this is it and you have to live with it. We're not happy with it, but it takes a while to get an update out for mobile devices.
Anyone else?
Thank you.